So far, the only types of polynomials we've really been looking at were linear and quadratic functions. So remember when we started out, linear was when we had our x and y axis, and it looks something like this, where it was just a straight line, right? We had our y-intercept, our x-intercept, and we could find the slope just calculating the rise over run. So however much it rises in the y direction divided by the x direction, we could get our slope, we could get our intercepts, blah, 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 right? And we could do a similar thing with quadratic equations, right? So quadratics had like this U shape of a parabola, and it was a bit harder to find the x-intercepts, right? We had to do some factoring, quadratic formula, all this stuff, but we had ways to figure out the intercepts, kind of how it looked, the characteristics of it. In this video, I'm going to generalize how we can identify the type of polynomial something is. So something that we haven't really talked about in the past is what cubic and quartic and quintic functions look like. So cubic functions, they're kind of like a line where they start in one corner and end up in another, except they just have two more turns. So lines don't have any turns, but cubic functions, they go up, they typically kind of come down and then go back up like this. So see how they have two turns? The way you can identify the degree of a polynomial, and the degree is just the highest exponent on the x. So for a cubic function like y equals x cubed, right, our exponent's 3. The way you can predict this exponent is to look at how many turns the graph has and add 1. So for example, this graph has a turn right here and a turn right here. So it has 2 turns in total, and we can expect this to be a cubic function. Okay, let's do another example here. Let's say we have a function that looks kind of like a W, like this. So it's kind of like a quadratic, except it has 2 more turns. Okay, it still ends up in the top left and the top right. So there's going to be 1 turn here, 1 turn here, and 1 turn here. So there's 3 turns in total, right? So we can expect this to be a quartic function. So x to the power of 4. Now there might be like a 2 in front here and then like plus x cubed minus 1 or something like that. But we know that it's probably going to be x to the 4 in terms of its degree. The degree of a polynomial is just the highest number in the exponent of your variable. Okay, one more example might be something crazy like that, right? So there's going to be 1 turn, 2 turns, 3 turns, 4 turns. Okay, so there's 4 turns. That means we can expect this to be a quintic function, so y equals x to the 5th. And like I said, there could be like a 5 out in front, minus 2x to the 4th, blah, blah, blah. But we know the highest degree can be 5 at the most. Okay, another way we can figure this out is to find how many intercepts it has. So instead of counting turns, we're going to count the intercepts. So there's 1 intercept here, 1 intercept here, 1 intercept here, 1 intercept here, right? And also 1 intercept right here. I didn't extend this long enough, but right here. So the degree of a function is just the maximum number of intercepts it can have. So this has 1, 2, 3, 4, 5 intercepts. That means the highest possible degree in your exponent for your variable is going to be 5. Okay, it can be, for example, it could be 6, right? It could be 7, but it's not going to be 4. Because if it was x to the 4, we'd be leaving out a solution. Okay, so that's the minimum degree on the exponent right there. It's just counting how many times it crosses through the x-axis. Okay, so that's another way that we can figure that out. I'll get rid of this here. And another thing when we're talking about characterizing polynomials is end behavior. So end behavior is just how the function acts as it gets to a really small number or a really big number. So if we have a line like this is a positive linear function, meaning the a value or the coefficient in front of your variable is positive, so maybe it's like 2x, and it's linear because the exponent's 1. So this function might resemble 2x to the power of 1, or just 2x. So it starts low and ends high, And when you're talking about its end behavior, you could say as x gets really small, or in fancy notation, they say as x approaches negative infinity, right? As x approaches negative infinity, x gets even smaller and smaller and smaller, goes to the left. Then we can say y approaches negative infinity. Because as x gets really small, y also goes down with it. So as we go to the left, we're also going down to the bottom of the page, right? So that would be the end behavior for a positive even function. And when they say, or sorry, a positive odd function, meaning its exponent is odd. And this would be the same, for example, y equals 5x cubed. So this is a positive odd function, meaning its coefficient in front of the x cubed is going to be positive, and it's going to look something like this. It's going to start from the bottom left, right? It's going to start from the bottom left, come up, and then end up where the positive linear also ended up. So this would have the same end behavior. Even though it's a different looking function, it's still going to have the same end behavior. And this is the same for y equals x to the, or sorry, this is 5x cubed. This would be the same for y equals x to the 7th, right? There'd be 6 turns probably. So we'd go 1, 2, 3, 4, 5, 6, and we would go up. So there's all these squiggly lines, but what I'm trying to get across to you is that the end behavior is just where the function goes as x gets really small or really big. That's kind of the main idea. Okay, what about when it's negative, or what about if it's an even function? Okay, let's talk about positive even functions first. So y equals x squared. We know that that's going to look something like this, right? Y equals x squared. We're pretty used to seeing that. We've done lots of factoring, all this kind of stuff. But what if we had y equals x to the 4th? Well, this is just kind of going to be like a steeper version of x squared. So it's not going to have 4x intercepts. It's just going to have 1. And we say that this function here has a multiplicity of 4 when x equals 0, meaning that all of the roots are at one place. So 4 of the roots are at only one x value. If it had a multiplicity of 2 like x squared does, it means that 2 of the roots are at one place. Okay? It's kind of a weird idea, but we'll talk about it in a couple minutes. Let's say we had y equals x to the 6th minus 2x squared plus 1 or something like that. Okay, we know that x-intercept's 1, and we know the highest degree is 6, so there's probably going to be 5 turns in this thing. There could be less, but at the most there's going to be 6. Or sorry, 5. So we go 1, 2, 3, 4, 5 turns. So it's going to look like this. Okay, so just like x squared started high and ended high, x to the 6th also has the same end behavior because it's a positive even function. Okay. Now, what if the function's negative? So let's say we had y equals x cubed minus 2x squared minus 5, for example. So this is a positive cubic function, but let's say we had a negative out in front. Well, a positive version would look something like this. It would be y-intercept at negative 5. Okay, now if we had the negative version of that, so if we took the negative version of, whoops, I kind of didn't leave myself enough room here. Y equals negative all of this. All that does is it just flips it in the x-axis, so it's going to look like this. Right? It's just going to be the opposite. So everything's going to be flipped. And I didn't draw that right. I didn't draw it perfectly symmetric here. So it's going to look like this, come up, and then go back down. So it's going to be perfectly flipped in the x direction, or in the x-axis, this axis right here. Okay, so if we're talking about the negative version of something, the end behavior is just going to be the opposite. So if it started in the bottom left and went to the top right, well, if it's the negative version of that function, it's going to start in the top left and in the bottom right. Okay, and we can do this with like even the easiest of functions. So let's say we had y equals x. we know it looks like this. Okay, well, y equals negative x, we know that's just going to be reflected exactly opposite in the x-axis, so it's going to look like that. So for any positive odd function, it's going to start bottom left, end in top right. For any negative odd function, it's going to start top left, end up bottom right. Now let's take an example for x squared. Let's say we had y equals positive x squared. This is going to be a positive even function. It's always going to start top left and top right. And if we had y equals negative x squared, so if we have a negative even function, it's going to start bottom left and bottom right. Okay, let's just look at these functions here, look at some of the end behaviors and the roots. So we can predict the degree of this function by counting the turns like I talked about before. So there's going to be 5 turns, meaning this is probably going to be y equals some variation of x to the 6th. So this is going to be a 6th degree polynomial with roots here and here. So remember, the maximum number of roots that we can have is going to be 6. So that would be if the x-axis was like right along here, and it kind of crossed through every point, like right there, 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 there. That would be like the most case scenario to have the most roots, okay? But what we have right now is just 2 roots. We know it's 5 turns, so it's probably going to be x to the 6th. It could be higher, it could be x to the 8th, but that's unlikely, right? Because it's symmetric and we can kind of tell. Okay, now let's just look at this one over here. So this one's going to have how many turns? Well, we have 1 turn here, 1 here, 1 here, 1 here, whoops, and that's about it. So this is how many turns? 4 turns. So we can say this is probably going to be x to the power of 5 or some variation of it. Okay, and it has 4 x-intercepts, but notice right here, there's a multiplicity of 2, meaning that there's 2 roots right here. So anytime you have your axis and the line just skims the x-axis like this, that's a multiplicity of 2. So if we were graphing y equals x squared, there's a multiplicity of 2 when x equals 0 right at this point. So there's 2 roots right here. So I hope this video was helpful in characterizing polynomials. I'll be talking lots about how we can find the roots of these higher degree functions, all that kind of stuff, but this is just kind of an introduction, so I'll see you soon.